recording. Let me come along here. Let's quickly do a, that didn't work. Let's quickly do a, I'll do that. I'll try and do like a 45 minutes and then we'll see where we're at. And that's recording. So welcome. We're going to talk about vectors today. Vectors kind of come in a number of bits. We talk about vector diagrams, and they're incredibly useful. I've had situations where people have come to me with what seem like very complex math problems, and you do a vector diagram and the answer just falls out. And they're like, man, how did you do that? It's just vector diagrams. So don't dismiss them because they're diagrams. They're actually really, really useful. And then the next thing we start talking about is components, basically resolving a vector into an x, y, and maybe even a z component. And they're incredibly useful for doing things like projectile motion and the like. And then we do IJK, which is three-dimensional vectors. And they're really useful for bookkeeping and making three-dimensional problems quite accessible to us. So we do step by step by step. So we can say important ideas. We can say we can define any point in space using a system of coordinates. So Descartes basically had this idea about x, y, and z axes. A system of coordinates defines a frame of reference. Parameters are either vectors or scalars. If you measure something, it's either a vector or a scalar. We can sum vector parameters using vector diagrams. We can use trig to convert vectors into component vectors that align with specific axes, and that's a really, really, really important skill. That's going to keep coming back. And then we can use vector components to sum vector parameters. We can use IJK vectors to sum vector parameters that are in 3 dimensions. And that also is an important skill. This is going to be important in the short term, and this is going to be important throughout physics 1 and physics 2. So let's just begin. A scalar. Scalar has magnitude, that's size, but no direction. So temperature is a great idea of a magnitude. We don't say it's 53 degrees in that direction. We might say it's 53 degrees at this point. We might say it's 53 degrees hotter in that direction over there, but that's a vector gradient. We don't say 53 degrees in that direction or that direction or that direction. Positive and negative doesn't mean to say it's a vector, even though on the number line we had the direction of the vector as positive and negative. Just because we used it on the number line does not mean to say you can just look and say, oh, there's a negative value, it must be a vector. It's not true. So temperature is a good scalar, mass is a good scalar of the things we've done so far. And then examples of displacement, well, examples of vectors would be displacement, because there was a beginning and an end, and we went from the beginning to the end. There was a start and an end. It has a direction, has a size, but it also has a direction. Velocity, if you do that in a certain time, that's a vector. And an acceleration, if you change the rate of velocity over time, you'll have a change. Later on, we'll get to many other things, and we'll say, you know, is density a vector? No, it's just a property of material, so it's a scalar. We're not using them today. It's okay. So the big classic is mass and weight. Mass is not a vector. Weight is a vector. Weight is a force, and so it has a direction. So at the beginning, it's like, oh man, you know, oh, so now we're concerned about vectors and scalars, and we kind of always are, because we kind of treat them differently. So how can we divide up space? Imagine trying to fill a room with shapes that don't leave any gaps. Well, the most obvious thing is cubes. Yeah, that would fill the space. But it's not the only thing that you could use to fill the space. And so we tend to take coordinates kind of like for granted. We don't really think about them that much. A coordinate system is used to identify locations in space. A coordinate system must consist of a fixed reference point called an origin. You've got to have a starting point. So there's your origin in these two systems. And then we have a set of specific axes or directions. And in the Cartesian, named after Descartes, in the Cartesian coordinate system, we have x and we have y, and you could even have z in 3 dimensions. And in the plane polar system, we have an axis, and we measure from the axis. So we need a coordinate system which consists of a fixed reference point or an origin, a set of specific axes and directions, and then instructions. These are made up. These are not, you couldn't infer these. If you met aliens, they might have the opposite instructions. Like, we've decided that we'll put the x, if I have a position like there, I'll figure out its x component or coordinate, whatever, first, and then I'll do the y. So I put down 2 numbers, and I put down x first and then y. That's completely made up. You can't intuit that. It's just Descartes or somebody decided that, and ever since then we've just done the same thing. Meet a space alien, they might have come from a different thing where they might well have x, y, and z because it's a really fundamental thing, but they might just have different rules. Do the y first, then do the x. It's just made up. Then the other one is a plane polar coordinate system. What it basically is that in 2 dimensions we have an axis, and our rules are, first of all, measure the distance from the origin to your point of interest. And then tell me how many degrees it is away from the axis line we just drew. So this would be more like 40 degrees, and if the line was round here, it would be like 100 and 130 degrees, and so on. So always measure the distance from the origin, and then measure how many degrees around you go. I don't know if you can see it, but if I had a circle, and even if it was symmetrical actually, but especially if it wasn't symmetrical, can you see how, if you imagine your x and your y's, you may have a whole list of x and y components for coordinates for this circle and not even recognize the part of a circle. Because the x's are changing and the y's are changing, and there's not trivial to find out why. But if I have a circle, especially if it's lined up, can you see my value is not going to change? My R value is going to be constant throughout, and my angle value is going to increase steadily. So you tend to spot straight away, oh, if I have a list of plane polar coordinates, I can spot the circles easily. But if I have Cartesian coordinates, I can't see the circles easily. Plane polar coordinates we tend to use more often when we're doing circular stuff. And Cartesian we tend to use more when we're not using circular stuff. It turns out to go from 2 dimensions to 3 dimensions in the Cartesian coordinate system is kind of nice, because you have basically axes that are 90 degrees to each other. So that's 90 degrees to that, and that's 90 degrees to that, and that's 90 degrees to that, and we have 3 dimensions that are independent of each other. To do this in 3 dimensions, then we start having to worry about stereoradians and stuff like that, and it gets messy. So we don't. I mean, we tend to not go where there be dragons, so we don't. There's a little thing I can do, which I say a point represented by 3, 4 in the Cartesian coordinate system expressed as a plane polar coordinate system. And what I'm doing is I'm kind of, in a way, I'm checking on your visualization and your trig. So 3, 4, 1, 2, 3, 1, 2, 3, 4. So there's my point of interest. I want to represent it on the Cartesian coordinate system. The first thing I have to do is figure out this length. And so I recognize, oh, it's Pythagoras. So I can say, r squared is equal to x squared plus y squared. There's x and there's y. So this equals 3 squared plus 4 squared, which equals 9 plus 16, which equals 25. So r is equal to the square root of 25, which equals 5. And frankly, this is so a lot of teachers are kind, and they kind of go, rather than having them do all this, Pythagoras, I'll just give them a 3, 4, 5 triangle. And it's great if you spot it. If you don't spot it, you don't get the benefit of it. But if you see a 3 and a 4 in a right triangle, you know the hypotenuse is 5. And then what's this angle? Well, this angle, so you sound and say, well, you go tan theta is equal to y over x, which equals 4 over 3, which equals 1.3 recurring. So theta is equal to tan to the minus 1 of 1.3 recurring. And somewhere I have my calculator. And what do I do when I'm doing anything to do with angles or the like? I always check to see what my mode is. And on these little handy-dandy calculators, it actually tells you, so I can look at this and I can see I'm already on degrees. And so second tangent, and I'm going to do 4 divided by 3, so then I have to worry about the recurring. And I'm going to get 53.13. So there's my angle, there's my length. I didn't have units in it. Shame on me. Should be in everything in meters. So 5 and 53 degrees would be my answer. So just a little double check on. It's a nice way of checking. Do you know what the definitions are, and can you do some math? But what I really want to get to is vector diagrams. Vector diagrams are incredibly abstract in a way. We start off typically talking about maps because they're not so abstract. If I'm dealing with a map, then here's the United States, and here's the Great Lakes, and I can imagine flying from Tampa to New York, and that would be an arrow pointing from Tampa to New York. From Tampa to New York, there's New York, and there's Tampa. And I can imagine going, that's 1,300 miles. I have no idea how far it is. And I can even give you a compass bearing, a direction. Got to give you both, a direction and a magnitude. It makes pretty much sense. But it doesn't have to be a vector in an XY diagram. I could have a force diagram where I have positions in space, X and Y, but now I'm not dealing with distances, I'm dealing with 7 newtons or 9 newtons. That's a little bit abstract. Forces point in a direction. They don't have a length in a direction. So I'm using an imaginary arrow that's 7 units long to represent the length of that vector. This is an actual measurement. This is how far you go. That's a displacement vector, but it actually takes up distance on your actual diagram. This is, in terms of X and Y, the head of the arrow is not over some other point of my machine. It's just pointing in that direction. So it's a bit of an abstraction. And I could have, for example, acceleration, 5 meters per second squared. In that direction, the acceleration doesn't have a length. It's just got a direction. So it does get a little bit abstract when you think about it. And so there's always that disadvantage that when a student doesn't think about it, they don't get confused, but they don't really make much progress. And the student that thinks about it does get confused, but if they get through the confusion, they make progress. So I always want you to think about it, but recognize the fact that you may get a little bit confused when you start digging deeper because you've not got all the It's like you're doing a jigsaw and you throw all the pieces on the table and you're starting to put them together. You could just look at it and say, oh yeah, look, Eiffel Tower. Look, there's a picture of the Eiffel Tower. It's like a bit messy, but it's the Eiffel Tower. Or you can try and say, well, that piece goes with there, and that piece goes with there, and that piece goes with there. And it gets a bit confusing. But if you stick with it, so it's a really nice picture of the Eiffel Tower. And that's what kind of we're about. Yeah, you can be superficial about these things, and nothing will occur to you that causes any confusion. You might not be very powerful, but, if you dig deeper, the danger is you'll get, oh man, I don't follow this. Yeah, you don't. So you've got to put some more work in and it'll come a bit easier. You overcome those things. So what's the skill here? The skill is draw in a vector diagram and recognizing a vector has a magnitude and a length, and we just get a ruler and we just draw it. So basically I said, this diagram has a vector, doesn't matter what it is. It could be a velocity vector, v1 and v2, and it's got a certain length, 7 meters per second in that direction, and this one is 4 meters per second in that direction. What would happen if I added a 7 meter per second in one direction to a 4 meter per second in another? How could you even do that? Imagine I have a machine tool, and the base of the machine tool is traveling in that direction at 7 meters per second. And riding on top of that base is another gantry which goes that direction at 4 meters per second. What's the result for the very top piece? It's got a 7 meter per second in that direction, a 4 meters per second in that direction. It's going to go like that. So it has very practical value to it. How on earth can I figure out the answer? And the rule is, you draw an arrow to scale of your first vector, whichever you pick. So I'm going to go 1, 2, 3, 4, 5, 6, 7. And the process of addition, use a diagram to find the resultant. That means add them together. The process of this addition is obtained by putting the tail of the first vector on the head of the second vector. So you literally get your ruler. You put your ruler here, and you slide it until your ruler is like that, and you draw another line. And then you go 1, 2, 3, 4. Shame on me. I meant the arrowhead when I should have just... Yeah, thought that might happen. So I draw a line, and I count along, and I go 4. So there's my 7 meters per second. There's my 4 meters per second. And my answer, my resultant, is whatever that happens to be. So look at what I'm doing. I'm drawing my line, and I'm putting an arrowhead on it. I'm being really careful. Vectors have arrowheads. Lines have no arrowheads. Vectors have arrowheads, very clear arrowheads. And then the process of addition is I slide the tail of my other vector onto the head of the first vector, and I draw it. And then my resultant replaces these two. It's the equivalent of. So I draw a line going from the beginning of the beginning to the end of the end. It's a straight line. So that I don't get it confused, I prefer to put it as a dotted line. I make sure there's an arrowhead on it, because when I grade, I'm going to look and I'm going to say arrowhead with an arrowhead. I like it. Arrowhead, arrowhead. Is the angle about right? That's what I'm going to look at. Okay? So there's a pattern to these. Doesn't matter what they are. Displacement, velocity, acceleration, force. You just add them together that way. You got 5 of them, add them together that way. Draw the first, and then on the top of the first, add the second, and then the top of the second, add the third, and on the top of the third, add the fourth, on the top of the fourth, add the fifth, and then replace them with a line going from the beginning of the beginning to the end of the end, and make sure you put arrowheads on. That's addition. It's Doesn't matter what it is. Draw vectors in sequence, head to tail, with the appropriate magnitude and direction. The resultant vector extends from the tail of the first vector, the beginning of the beginning, to the head of the last vector, the end of the end. The order of the sequence that you use does not matter. You could change the order, you still get the same answer. You're just adding them together. This is great. I can do some really quite amazing stuff using this. What about subtraction? Can you subtract vectors? Yeah, you can. So how does this work? I only know how to add. Yeah. But I'll tell you what. The negative of a vector is the same magnitude as the positive of a vector, but it has the opposite direction. Plus 5, minus 5. Plus 2, minus 2. Plus 7, minus 7. Just the opposite direction. Plus A, minus A. Plus C, minus C. Just the opposite direction. So I do a bit of math trickery here and I say, oh, so the other thing is, when I was a student, vectors always had little arrows on top. So you knew it was a vector. Even the textbooks had little arrows on top of the vectors. And then when they started doing computer, typesetting, it took a while for the more sophisticated programs to come out. And people started saying, we can do bold letters now. So they just started replacing all these little A with a little arrow on top to just a bold A, which is great. But my pen doesn't have a bold setting. So when you're doing these by hand, you want to put arrows on top of them. And having gone through all my notes and changed all the arrowheads to a bold, I'm now wanting to go back and replace them all back into arrowheads because, we've got to learn to write this stuff. So that's a vector and that's a vector. So vector A subtract vector B. Vector A minus vector B is vector A added to minus vector B. Now you know that mathematically. Arithmetically you go 4 minus 2 is the same as 4 plus minus 2. Yeah, you know that mathematically. But it also is vectorially. So using vector diagram, find B minus A. So the first thing is I've got to do B first. So I'm going to do my B. And what I'm looking for is, you get a ruler or you get a piece of paper and you lay it on there and you kind of mark it and then you slide it across and you lay it on there. So you get a decent length for it. It doesn't have to be to within a fraction of a millimeter, but you get a decent length. And you're going to mark that as B. And then, of course, I put it right where I want to do my next step. So that's going to be minus B. I'm sorry, that's going to be plus B. And then if I was adding A, I'd do that line and I'd go that far along because that's A, agreed? But I don't want to do minus A. I don't want to do A. I want to do minus A. Opposite direction. So minus A. And my resultant goes from the beginning of the beginning to the end of the end. So what I'll look for is, did you draw B in the right direction, about the right length? Did you put an arrowhead on it? Did you draw A? About the, minus A, about the right direction, about the right length. Did you put an arrow on it? Did you put your resultant from the beginning of the beginning to the end of the end, and did you put an arrowhead on it? Most common mistake, people forget to put the arrowhead on the resultant, or they're not prepared to commit one way or the other. Or they put it in the wrong direction, they complete the circle, which is bad. Or people kind of like, they just get confused, and it's like not anything like it. So a question, yeah.
Do resultants have negative magnitude?
So none of them, not anything here has a negative magnitude. even that minus a is a positive magnitude in a negative direction. Okay, so it's kind of like it's very interesting, yeah. But all vectors have a positive magnitude because they've got to exist. But they can point in different directions. And we define that as positive and that as negative, or that as positive and that as negative, or that as positive and that as negative. It's all relative. Yeah. What about multiplying? Oh, if it's 3a, so this of course is vector A, and this is vector A, and this is vector A. Draw a line 3 times longer. That's 3a. So this is vector A, and this is vector 3a. Half a, draw a line half as long. Okay. So characterize the following as either Cartesian or polar coordinates. So let's have a look. We have Cartesian coordinates. What's it going to be? That's going to be Cartesian. Agreed? Polar. Polar. Cartesian. Yeah? So, that guy, yeah. Question or? No.
About polar coordinate, I know how to that we have the negative r, the negative radius. So is that correct?
I've never come across a negative radius.
Because, well, for example, like if r is 3 and the angle is like 30 degrees or something, it's going to be in the first quarter of the.
So yeah, so I would go 3, 30 degrees.
Yeah, it's going to be the first quarter.
So there's its magnitude, and there's its direction. Oh, so you're saying if I work out the cosine or the sine of this, is that what you're saying?
No, let me keep going like that.
Okay.
It's like negative 3 and 30 degrees. It's going to be on the opposite direction.
Oh no, I would prefer you to put down 3, and you're going to put down 210.
But it's going to be the same, right? If
I would prefer you to put it down this direction because I don't like the idea of negative magnitudes. I know mathematically it's the same, but in physics, I think there's something pure about components, about magnitudes are positive. Okay. So, yeah, if you put down minus 3 and 30, I think that would be, well, I'd have to think about it. I know what you're doing. You're kind of going like that. You're going, okay, well, there's 30, but I'm not going in that direction. I'm going in that direction. So you end up the same as 3, but I think that's the better way of describing it. Okay. Unless the math teacher has a really good argument. But maybe they can teach me a thing or two, but I've never thought of it like that. Using a vector diagram, find the resultant of these displacement vectors. Who's got a ruler with them? If you've not got a ruler with you, I'm going to show you. I mean this in fun. I'm going to tell you what the teacher called it with me, but I mean this in fun. I'm not being insulting. So this is called a slacker ruler. It's kind of nice. But you take a piece of paper and you fold it up, and you fold it again. Okay? It's a ruler. And then what you do, and what I'm going to do is I'm going to show you on the overhead projector so that you can't actually see this. So I'm going to pause this guy. So welcome back. We're going to do these kind of like so we can see them on the video. So the first thing I do is says find the resultant of these displacement vectors. So the order doesn't matter, but even so I'm going to try and stick to the order. So I'm going to go, well, there is my A. And I would use my little ruler and I'd slide it across the page and make it about the right length. And then I would add on my B, again, sliding the ruler across the page. Most common mistake is people either they forget to put the arrows on, or they leave me that, which is not the answer. You've got to tell me what the resultant is. And the resultant is the overall effect, which is you start at the beginning and you end at the end. And so I look for, when my grading, I'm looking for, is this arrow, is the shape right? Is this arrow right? And does it have an arrowhead on? I got to be able to see the arrowhead. All that business, forget it. I'm blind as a bat. You got to make it so that, you know, it's like, yes, there's an arrowhead on it. And the same goes for these guys. Cool? Using vector diagram, B minus A. So let's have a look. B is the first thing, so let's just draw B. And then minus A. Well, A is in that direction, so minus A must be in that direction. Yeah, this is B. This is minus A. A was in that direction, minus A is in the opposite direction. Do your resultant. So they're not long, they're not time consuming. You just got to get into the pattern of it and not fall into that trap of either not putting arrowheads on or not having the arrowheads in the right direction. And it's one of these things where unfortunately people look at it and they go, that's a piece of cake, and they don't practice, and then they get to the test and they make a slip like that. This is A. And then 3B. Oh, there's 1B. There's 2B. And there's 3B. This is going to be 3B. Okay. Make my arrowheads real big. So you can see how it's going, yeah? 2A minus B. Oh man, I messed up, didn't I? Minus B. So my resultant and you know, it's sometimes hard to get them in, but I'm going to make sure that, you know, the tester can see that I have arrowheads where I need them. Yeah. There we are. Expect one of those. It's easy points. Just practice and you get it. Next. Vector components. The problem with vector diagrams is that if we all did our diagrams, even with a ruler and a protractor and the like, and I laid them on top of each other, I'd find that there'd be a fair amount of disagreement about this first point, and even more about the second point, and even more about the third, and even more about the fourth, and even more about the fifth. Because what happens is we all start just slightly variation on the first point, gets bigger and bigger and bigger as we go on. So the more steps, the more problematic my diagram is. Just more inaccurate it is. I mean, remember, you know, 50 years ago, people used to navigate across continents using just, you know, a compass, a set of charts, and a vector diagram. That's what they did. They'd basically just draw vector diagrams and then make their way. But they wouldn't do it for that far. They'd say, let's go for, you know, 300 miles and we'll look for this city. Oh, there it is. Okay, so now we realign and then they go off. So they're doing, what is it, dead point reckoning or something like that. We need a better way. I can do math on this. I mean, I'm sure your math teachers have taught you how to do stuff like this, where you have these big and small angles, and you can figure it out. But it's a bit like my daughter's math, where it's like a page to do something that there's an easier way of doing it. So it's not impossible, it's just tedious. And the chances of making a mistake are great, because you're just not used to working with, you know, you take that and you know that angle and you know that length, so you can kind of figure out where that point is. And then you got another angle from the original length, and you got to, so it's very much difficult keeping track of where you are. You can do it, but it's a real pain. along came somebody, I don't know who it was, but along came somebody with a bit of a brainwave. And they said, the problem is all these angles are kind of relative to each other. They're not relative to the underlying coordinate, pattern, the Cartesian coordinate pattern. So why don't we redo this? And why don't we do it so that every vector gets broken up into two components, one in the x and one in the y. And we get really good at that. That's trig. And then we simply add all the x components together. We get the x component of our answer. We add all the y components together. We get the y component of our answer. We know the components of our answer. We can find its magnitude and its direction quite easily. So we're doing this like formulaic little step on everything so that we can add arithmetically and then just do a little bit of Pythagoras at the end and we get our answer. And in fact, after a while, you get to the stage where you can think in terms of the coordinates. You don't really need to know the distance. If I tell you that it's 5 meters along the x and 7 meters along the y, you kind of know where it is. I don't need to get you to work out the actual true distance and the angle because you can work in components. Why not? But we'll go through it. So basically, what we're doing is we're saying for every vector that we get, we're going to practice working out its x components. So this is the point of interest, or this is the vector of interest. Let's put it like that. This is the vector of interest. And I'm going to break it up into a horizontal vector and a vertical vector to replace the original. Let's say I'm a pilot and I never got the hang of doing compass bearings. I get confused. So my way of going to New York City from Tampa is not to fly for 1,300 miles at, 74 degrees north of east. I go 600 miles due east, and then I go 900 miles due north. I get there in the end. I use more fuel, it takes longer, but hey, it's a lot easier for me. I just go east-west, and then I go north-south. It's a piece of cake. It's the same effect. Might not be as efficient, but it's the same effect. And that's what we're doing. Rather than doing the direct route, let's do the two component routes. And so in reality, what you do is you do that, and then you do that, but we tend to represent them as one on the x and one on the y, from the origin. And how do we get this? Well, we're using trig. What we recognize is that length there, well, that length is an adjacent, and the A is always the hypotenuse. So this is going to be A cosine the angle. And this here is the same as that there. So that is A sine the angle. So let's just stop a little bit. So for a triangle, we have an opposite, we have an adjacent, and we have a hypotenuse. And we know that SOHCAHTOA, sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. SOHCAHTOA, yeah? So when I was in the high school, I used to collect ways of remembering that, because for a lot of them it was the first time they'd come across it. So you do guys know SOHCAHTOA, 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 to remember it. And then there's like that, some old horse caught another horse taking oats away. Did you hear that one? It's like, you just got to know these fast. This is not about the trig. The trig is going to be like adding up. So however good you are, if you're not fast at it, you've got to get faster. And the dilemma is that we show you it with a nice coordinate system. X is horizontal, Y is vertical, we give you the angle to the X. And the danger is you think, oh yeah, X is always cosine and Y is always sine, because in this diagram it is. But supposing I give you that angle, then the X is the sine of the angle and the Y is the cosine of the angle. So I just changed everything by giving you the other angle. The complementary angle, I just changed what's a sine and what's a cosine. Yeah? And the fact is, very soon we're going to be doing, and you're going to find the component down there and the component down there. So it's going to be upside down and backwards and all that. And you cannot be going, what was it again? Some old horse, Scott. You've got to just like know. You've got to be able to look at it and know it. And you don't come out of trig with that level of skill because you're doing so much other trig. You're on this for a bit and then you leave. But this is what we need. So you've got to practice it. Okay? And you've got to practice when it's not lined up and when it is lined up and all that. So we say, well, okay, the original vector is equal to the x component vector plus the y component vector, and the x component vector equals a cosine theta, and the y component vector is a sine theta in this diagram. And once I've got my two components, the magnitude of the resultant is equal to the Pythagoras of this distance and that distance squared, distance squared and that is squared. And this angle here is 10 to the minus 1 of it. And we've got to practice it. So a football has been kicked 10 meters per second on line. So draw yourself a little thing. 10 meters per second. Draw it big. Most people do little diagrams and 30 degrees angle to the elevation. If you're not used to drawing diagrams, I would love it if you got out your protractor and drew that at 30 degrees. Eventually you don't have to. But the problem is when people first start, this is what I see. I see a little diagram. I see that. I see 10. I see 30. And that's going to walk you off a plank. Because first of all, that's 45 degrees. It's not 30 degrees. 30 degrees is less than halfway. So this is the small angle. That is the big angle. There's no small angle and big angle in this thing. So my advice is draw big diagrams, especially at the beginning, and use your protractor to get the angles about right. And your diagrams will just be a lot more informative to you. So football is fired at 10 meters per second along a line at 30 degrees angle of elevation above the horizontal. What is the horizontal component? So let's visualize. That is my horizontal component. I'm going to change colors so that you can see my visualizing. I'm going to put it in red. So this is my horizontal component. That is what I'm looking for. That is an adjacent. The 10 is a hypotenuse. If you want to begin with, you can say cosine theta is equal to opposite over is equal to adjacent over hypotenuse, which equals, and then you can say, oh, in that case then adjacent is equal to h cosine theta. So adjacent is equal to, you look at your diagram, you go 10 cosine 30. But I want you to get to the stage where you can just say, oh, this is going to be AX. AX is equal to 10 cosine 30 degrees. Because you're going to be there. You're going to have to be there pretty soon. And then you get your calculator and you work it out. 10 cosine 30. And it's going to be 8.66. Cool. Yep. You got a question? Are you okay? You guys okay? Okay. So, give you a tip. If you hold your hand like that, and you put your fingers on one side, say the hypotenuse that you know, and your thumb on what you want, and you're using the angle in between, it's a cosine of the angle. If you put your fingers on what you want, and you put your thumb on what you have, or vice versa, whatever it is, and you're not using the angle in between, suppose I use that 60 rather than that 30, it's a sine of the 60. Cosine of the 30 is a sine of the 60. So if you do that, where you say, I want this, I got that, I'm using that angle, it's a cosine of that angle. Doesn't matter. I want this, I want that, I'm using the angle, it's a cosine of that angle. You can have it in any orientation. I want this, I got that, I'm using the angle in between, it's a cosine of that angle. And then if I'm not using that angle, I'm using the complementary angle, the thing that adds up to 90, is that the right word for it? If I'm using the complementary angle, then it's the sine of that complementary angle. That's a good tip. And the other tip I'll share with you, and this is gold dust. This took me, at least a month to figure out. We didn't get testing like you guys got. We got tested at the end of the year. So you could be lost for a month. And in a way, it didn't matter, but in another way, you kind of like weren't worried about it, so you didn't really dig your way out very quickly. The other thing that took me a while to figure out is that the original vector is always the hypotenuse. It's always the hypotenuse. And it seems obvious here, but as I say, when you get a situation where you have a block and it's there, and you have this thing down there, and you're trying to find the down the slope component, it's very easy to draw it like that, and it is wrong. Not because you don't know your trig, but because you don't know your diagram. That original vector is always the hypotenuse. Always. You always approach the component at 90 degrees. It's always that shape. Problem here is between the original vector is not my hypotenuse. My component is longer than my original vector. It cannot be. And that's so obvious they don't put it in the books. But it wasn't obvious to me. So half the time I'd get them right, and the other half the time I'd get them wrong, and I'd practice my trig, and I knew my sine, cosine, and tangent. And it was because I was drawing the diagrams wrong. And then finally it dawned on me that, the original vector is always the hypotenuse. The components have to be smaller than the original vector. It makes sense when you think about it. And, I've drawn my diagrams wrong. And then I started getting them all right. So that was like, that was like so, it was like pulling skin trying to find out what I was doing wrong. Because half the time I'd get them right, and half the time I'd get them wrong, because it was like inconsistent. So never, 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 never. And can you see how when you're working at some angle, it is more confusing. What is the angle of elevation of a rooftop when it has a horizontal component of displacement? So the horizontal component of displacement is 10 meters. And a vertical component of displacement, so that, which is the same as that, is 20 meters. There's my rooftop. I want to know that. So what is the angle of elevation? Well, if that's 20 meters. I'm going to say tan theta equals opposite over adjacent, which equals 20 over 10, which equals 2. So theta equals 10 to the minus 1 of 2. Theta is equal to. Second tangent, 2. And I'm getting 63.43 degrees. Yeah, 2 more and then we'll take a break. Let's say we've done that for all our vectors. We added up all the x's, we added up all the y's. We ended up, let's say let's say this is our vector. I want to figure out what my x component is, that's my ax, and I want to figure out what my y component is, that's ay. These are magnitudes. How big is ax and how big is ay? Well, from trig, I can say that ax equals 7 cosine 25. Can you see it? Adjacent over hypotenuse is a cosine. So adjacent equals the hypotenuse times the cosine of the angle, 7 cosine 25. And ay, which is the same as this opposite, ay is equal to 7 sine 25. And again, I'm still giving you the angle to the horizontal, so I'm kind of lulling you into a false sense of security. So this would be 6.3. And this would be 7 sine 25. And that's going to be 2.9. Or 2.95. So, yeah, 2.95, which equals 3. So it's that guy. Yeah. Let's say we've added all our components together. We added all the x's together. We got positive 6. We added all our y's together and got positive 4. Then what is the answer, the resultant? What is the magnitude and direction of the resultant? Okay, you're just going to say, oh, r is, that's the vector r, but r is equal to the square root of 4 squared plus 6 squared, which equals the square root of 16 plus 36, which equals the square root of 36, 46, 52. So r is equal to the square root of 52, second square root 52, 7.2 meters. And then this angle, tan theta is equal to opposite over adjacent, which equals 4 over 6. So theta equals tan to the minus 1 of 4 over 6, which equals second tangent 4 divided by 6 parentheses. And I'm going to get 33.69 degrees. That's going to be 33 points. Whoa. I'm a little bit out. 7.2. I got 33.4, but that's a bad. That's the answer, but it's that guy. Okay. We're going to be doing this for like a month, using this in more and more forms. So look ahead and recognize you just got to get skillful with your components. I'm going to stop it there.